Hello, student. Welcome back to this topic of magnetoelectric composites and their applications. So, in the last class, I have explained the importance of these two effects. They are the piezoelectric effect and the magnetostriction effect. So, we are combining these two effects to get one single effect that is called as the magnetoelectric effect. So this magnetoelectric, this piezoelectric effect and the magnetostriction effect both are very, very important in this phenomena of magnetoelectric composites. So these magnetoelectric composites are generally called as multiferroics or simply magnetoelectrics. Here, this term multiferroic comes because here, especially the iron will be existing in more than one valency state. So because of that reason, this is called as the multiferroics. And this is a linear or non-linear phenomenon because here the magnetization in ferromagnetic material is controlled by the electric field, and the polarization in the piezoelectric material is controlled by the magnetic field. So here this cross-linking of this magnetic field and electric field and the magnetization in the ferromagnetic material and the polarization in the piezoelectric material cross-links together to give us a new effect that is called as the magnetoelectric effect. So this cross coupling results in a change in P. P means polarization due to an applied magnetic field, which we are calling as the direct ME effect, and a change in magnetization M, capital M, due to an applied electric field that is called as the converse effect. So in this case, both the magnetic and electric properties can be mutually controlled. Such materials these are. So here, I will explain how we are getting this XZ effect or the magnetoelectric effect. So in the diagram, you can see here phase one material is there. So here, phase one material is generally a ferromagnetic material. And what happens to this ferromagnetic material, or sometimes even it can be a ferrite material, which is a ferrimagnetic material. Ferrites are also used because as compared to the ferromagnetic materials, ferrites are having a higher resistivity. Because of that reason, ferrites are more prepared than the ferromagnetic materials. So most of the time, this phase one material will be a ferrite material. So when we are applying the magnetic field to this complex mixture of two phase materials, what happens? The phase one material will respond to the input. The input is the magnetic field. So magnetic field is the input for this phase one material. And because of the magnetostriction effect, which is going to take place in the magnetic material, a stress is developed on the phase two material. So this phase two material is generally a ferroelectric material, and the materials such as the barium titanate and the lead zirconium titanate are used since since they can produce the higher level of or the higher magnitudes of the piezoelectric effect, because that is very, very important for us. So that is why what happens, a stress is induced on the phase two material. So this induced stress becomes input for the phase two material, and this is the output of the stress developed is the output of this phase one material. And this input to the phase two material, which is a piezoelectric material, the piezoelectric effect takes place. So that means there can be some changes. That means that piezoelectric material start developing the charges over its surface and leading to the development of an electric voltages. Of course, a small voltage is developed across the phase two material. So that means the collection of charges over the surface of this phase two material will lead to electric field, some voltage, as well as some electric field is created. So electric field is the output. So here we have inputted the magnetic field, but we are getting electric field as the output. So these two. So this is let us say we can call this as a XY effect, and this is the YZ effect. The combination of these two will give rise to XZ effect. So in this way, we are getting a magnetoelectric effect due to the combination of two phase materials which are coexisting together. So interlinking of different fields. Let us see what is the interlinking of different fields. So you can look at this diagram. So this green color circle is there. This green color circle. It consists of the magnetically polarizable spins or the magnetic dipoles. We can say that the magnetic dipoles are present here. And this blue color circle shows that that is the region where this ferromagnetic material is there, ferrimagnetic material is there. And similarly, on other side, this pink color circle indicates the presence of the ferroelectric material, and this red color circle indicates the presence of the electrically polarizable things. So they are the electric dipoles are there. So all these circles are overlapping one over the another. So here you can see this overlapped area where the ferrimagnetic material is overlapping the ferroelectric material. So the fields, internal fields of the ferrimagnetic material and ferroelectric materials are overlapping one over the another, leading to the interlinking or cross-linking of these two fields. So here also you can see, so this region where these two fields are linking together or cross-linking together, we can say that that is the that leads to the ME effect. And here also you can see this yellow circle, yellow colored circle is there. There is a cross-linking of the fields developed by the magnetic dipoles and electric dipoles. So this area, this region shows that or shows the magnetoelectric effect region. So when the composites are formed, we are mixing two types of materials. One is the piezomagnetic material, which is generally a ferrimagnetic material, Another one is a piezoelectric material. That is the generally a ferroelectric material. These two materials are mixed together to get this kind of a common effect, which is called as a multiferroic material, multiferroic effect, or the magnetoelectric effect. So here are I am going to discuss some requirements for good ME composites. These requirements are for either a ME composite or in general any composite. For any composite, these conditions are to be satisfied, and these requirements are first time outlined by the Boomgard et al. And they are holding good, or they are valid for any composite in general. So to get a good ME effect in the composites, what we have prepared, we should take care of all these things. So the first point here tells that the individual phases should be in equilibrium, and there should be no chemical reaction between them in the composites. The chemical reaction between constant phases and their starting materials during sintering process may reduce the piezoelectric or magnetoelectric properties of the phases. This results in the reduction of resistivity as well as the ME output. So this is very, very important. Both the phases should be in equilibrium, and there should be no chemical reaction between them. Chemical reaction means actually here, no exchange of electron is taking place between the phase 1 material and phase 2 material. So phase 1 material in this case is a ferromagnetic material, whereas the phase 2 material here is generally a ferroelectric material. So when these two materials are mixed together, there should not be no chemical reaction between these two. That means no exchange of electrons is allowed between the ferromagnetic materials and the ferroelectric materials, because once the chemical reaction takes place between these two phases, another phase, third phase will be evolved, and you will not get the ME effect. So that is the point. And next, the second point is that there should not be any mismatch between the grains. So this is very important, but it is very difficult to achieve also, because here when we make the composites, these two phases are prepared separately. That means the ferromagnetic material is prepared separately, and the ferroelectric material is prepared separately at different conditions and at a different sintering temperatures. And because of that reason, what happens? The grain growth in the ferrite material will be different, and the grain growth in the ferroelectric materials will be different because of the chemical composition. So that is why most of the time it is a very difficult task to achieve a grain matching between these two phases. If they are nearly equal, we can say that this ME effect produced will be more. So that is the meaning of this point. And next, to ensure good mechanical coupling between the particles of the constituents, the mechanical defects like pores or microscopic cracks formed due to lattice strain at the interface should be as low as possible. So these pores and microscopic cracks formed in the composite material will definitely going to hinder the properties of the ME composites. So the care should be taken that the porosity level will be at a minimum level, and we have to maintain a high density and a high purity of the materials. So that is very, very important. And this lattice strain will be produced because we are having one sensitive, strain sensitive material, that is a ferroelectric material is there. That is a very, very strain sensitive material. So if pores, all those things are formed inside the composite material, so some properties, you will get some different properties because of this lattice strain produced in the composite material. And next point is that the magnitude of a piezoelectric coefficient of a piezoelectric phase should be high. So we have to use one piezoelectric material, and the magnitude of the piezoelectric coefficient of that piezoelectric phase should be as high as possible, so that at minimum applied electric field, we are getting a more piezoelectric effect. So that is a very, very important point. And the magnitude of magnetostriction coefficient of magnetostrictive phase should be high. So the other phase is the magnetostrictive phase. That means ferrite phase. So so for the ferrite phase also, we have to choose a ferrite phase in such a way that more magnetostriction is produced at a lower application of the magnetic field. Such materials are very, very important for this for this production of magnetoelectric effect. And we will move to the next point. That is the resistivity of a magnetostrictive phase should be high. So when we compare the resistivity of both the phases, that is ferrimagnetic phase and the ferroelectric phase, as you know, the ferroelectric phase is generally having the high resistivity as compared to the ferrimagnetic phase. Because in case of ferrimagnetic phase, iron is there, and iron is a highly conductive material, and because of that reason, the resistivity of the ferrimagnetic phase is generally low. Whereas in ferroelectric material like barium titanate or the lead zirconium titanate, iron is absent. So because of that reason, the ferroelectric material will be generally having more higher resistivity values as compared to these ferromagnetic values. So that is why we have to choose the metal ions present in the ferromagnetic phase in such a way that the resistivity of the ferromagnetic phase is high. And for example, how to increase the resistivity of the ferromagnetic phase? The simple idea is that by experiment, or by our earlier experiments, our work on the ferromagnetic materials, it is very clear that the substitution of the metal ions like magnesium will lead to increase the resistivity of the ferromagnetic material. That is the point. And the next, the electrical poling. If the resistivity of the ferromagnetic material should be high, the electrical poling becomes difficult, and the MU properties get reduced because of the leakage currents if the resistivity is low. So here, suppose if the resistivity of the ferromagnetic material is low, what happens to this ME effect? So that is the question. So this electrical poling, I will discuss this phenomenon in detail. Electrical poling means we are keeping the composite in an electric field in a particular direction, that is called as the electrical polling. And if the resistivity of the ferromagnetic material is less during the polling process, the leakage of currents will be there, will be flowing in the circuit. So what, because during the electrical polling we are applying the very high electrical field, so that high applied electrical field may lead to the flow of this leakage currents through the Faraday phase. So in order to avoid that, we have to increase the resistivity of the this magnetostrict phase. That is very, very important. And to ensure proper polling, transition temperatures of both the phases must be greater than the room temperature. So generally what happens during the polling process, electrical polling process, what happens, there can be some release of temperature, heat energy in the composite because of the, and suppose if the transition temperature both the phases is low, then both the phases will lose their fundamental property, that is the ferromagnetic nature of ferrite and ferroelectric nature of the titanates, lead zirconium titanate or other titanates. They lose their fundamental property. So because of that reason, we have to take care of this transition temperature also. This transition temperature is actually, it is a Curie temperature, and below that temperature, the materials hold their ferromagnetic nature or the ferroelectric nature. And proper electrical and magnetic polling strategy should be adopted in composites to obtain the higher ME output. So electrical polling, as I told, that is the keeping a composite material in a high electrical field in a particular direction is electrical polling. Similarly, magnetic polling is there. That means before measurement of this ME effect, the materials will have to be poled electrically and magnetically. And even during the magnetic polling, that means you have to keep the composite material in a magnetic field in a particular direction. The direction of polling is also very, very important. Then I will come back to this historical background of ME materials. That means the magnetoelectric materials. The concept of this ME effect was first suggested by Röntgen in 1888. He discovered that a dielectric material could be magnetized when placed in a magnetic field. So this is the very igniting thought given by Röntgen in 1888. So first time he told that that the dielectric material could be magnetized when placed in a magnetic field. So that led to the invention of the ME effect. And in 1894, Curie suggested that some crystals have intrinsic ME effect. That means by origin, because of their crystal structure, all those things, and because of the presence of the different metal ions in a material, some materials are having the intrinsic or the original genuine ME effect. The term magnetoelectric effect was first used by Debye in 1926, and in 1926, after studying magnetic and electric induced changes in a dipolar paramagnetic molecules. That means the Debye was working on paramagnetic molecules, but he found that So the application of the electric field could doing some is producing some magnetism in the paramagnetic materials. So with this idea, this magnetoelectric effect was developed. And in 1960, Astro reproduced the first observation of magnetic field-induced electric polarization in antiferromagnetic single crystals of chromium oxide. So this is the first invention, practical invention by Astro in 1966, and he first time showed that electric polarization could be achieved in this anti-ferromagnetic material with the help of applied magnetic field. So later in this way, the research on this ME material started, and because of their interesting properties, the researchers has done a lot of work on these ME materials. And in the next session, I am going to explain the different types of EME materials. Thanks for listening.